So find two numbers whose sum is 300 and whose product is a maximum. So what we're looking for here is a number that when we add it to another number we get 300, but when we multiply those two numbers we get the largest possible number. So of all the positive numbers in the world that add up to 300, we're choosing the two that when they're multiplied together they give us the largest product. That means that no other two numbers are going to give us a larger product when multiplied. Alright, so we're going to call the two numbers x and y. And we know that by definition that means that x plus y is 300, and x times y, we're going to call that maximum. Now when we say x plus y equals 300, that means that y can be written as 300 minus x. So when we see xy, that's really going to be x times 300 minus x equals maximum. So we're going to call this thing a function. X times 300 minus x. And we know that can be written as 300x minus x squared. And remember what it takes to find a max or a min in a function. We have to find the derivative, set it equal to 0, and then come up with the critical numbers. And at those critical numbers, that's where the extrema occur. This is a parabola that opens down because it has a negative x squared as the highest degree, degree 2. And that means that it's only going to have a maximum. It can't even have a minimum. So the derivative here is going to be 300 minus 2x. If we solve for x, we end up with 150. Now we're sure that that is going to be the maximum point. And so if we plug that back in and try to evaluate for y, we get 150 also. So that's pretty much a typical optimization problem. The next one is not a typical optimization problem. So a sailor is 2 miles offshore in a boat and wishes to reach a city 6 miles down a straight shoreline from a point nearest the boat. She can sail at 2 miles per hour and can walk 5 miles per hour. Where should she land her boat to reach the village in the least amount of time? So we have to come up with a picture of this thing, and the best way to do that is to draw a map of the boat compared to where it's going on land. So we have this triangulation here, but we're not really asking if she's going to go straight into land, which we know to be 2 miles. She's actually going to land somewhere between, if she were to go straight to land, and where that city is. So what that means is we want to come up with a point on land where that x is. It could be a little bit above that or a little bit below, such that when she lands there, it's going to be the least amount of time between sailing and walking to that village. So what that means, maybe if we put that x all the way down to where that city is, maybe it's a lot quicker if she just lands there and walks that little piece to the village. Or if we put it all the way up at the top of that triangle on the right below those trees, maybe that would be the place that would be quickest. So there's her route right there. So we need to figure out the lengths of those two lines. So what we know so far, we know the distance is equal to rate times time, always. And we know that that right there is 2 miles until she could land on land. We know that over here it's 6 miles from that point down to the village or the city. And what that means is from the point where she lands to the city, we can call that 6 minus x. And from the point where she lands up to where it would be a straight shot into the land, that's going to be x. So that's how we can break up that 6 miles. So that line right in the middle there, that's where she's going to be sailing in, and then she's going to walk the rest down there. So the sailing distance, we can use the Pythagorean theorem. That's going to be the square root of x squared plus 2 squared, that top triangle. And the walking distance, we know it's going to be 6 minus x. Okay, so we know that d is equal to RT, and we can solve for t. So t is equal to d over r. So now the time to sail is going to be the square root of 4 plus x squared over 2, and the time to walk we know is going to be 6 minus x divided by 5. So how do we know it's going to be 2 and 5? Well, 2 miles per hour to sail, 5 miles per hour to walk. So that means the time total to travel to that village, city, is going to be those two things added together. And now, since we have that total time, we want to call this thing a function. So there's our function f of x. And remember, all we need to do here in order to figure out what the max or the min time is going to be, that function is representative of time, is to find the critical numbers and plug that in, whatever that x value is, and find the y value. Okay, so our function, if we find its derivative, for the first one, remember really that 2 and the 5 that are on the bottom, they're just constants, we can pull them out. So for the first one, we're going to have 1/2 times 4 plus x squared to the negative 1/2 times the derivative of 4 plus x squared. And then minus, well, 6 minus x, the derivative is just negative 1. So what we need to do is find a common denominator after we set this thing equal to 0. So the common denominator is going to be 10 times that square root. And so I multiply the first fraction by 5 over 5, the second by 2 times that radical over itself. So when we do that, we end up here with the square root of 4 plus x squared is equal to 5/2. We want to square both sides. And that means that x squared is equal to 9 over 4, so x is plus or minus 1.5. So remember what this function represents. When we plug in x, which is a distance, we end up with the total time. We know distance can't be negative, and so we're going to look at just the positive version. So the sailor should land 1.5 miles down the coast and walk the remaining 4.5 miles. If we wanted to find the exact time it took, we would just plug in that x equals 1.5. So there it is. Okay, so we want to build a rectangular pen with 3 parallel partitions using, well, we only have 500 feet of fencing. What dimensions will maximize the total area of the pen? So we go to the store, we buy 500 feet of fencing, and we don't know how we want to build this pen yet, but we know we want it to be the largest possible area. So a picture of that is going to look like this. And so there are a few different ways that we can choose x. We're going to choose it to be the width of one of those pens, and then y is going to be the length. And so the total amount of fence that we have to build with is 6x plus 4y. So our perimeter is going to be 6x plus 4y. Our area is just going to be x times y, and remember that's what's going to be maximized. Okay, so our function is going to be x times y, and the perimeter we know is 500 is equal to 6x plus 4y. So if we solve for y, we end up with 125 minus 3/2 x, and that's what we're going to replace inside of the function. So if we distribute it, we're going to have 125x minus 3/2 x squared. And remember what we have to do now. Find the derivative and set it equal to 0. And when we solve, we end up with 41.67, or 125 over 3. And if we plug that in, we end up with 62.5. So there are the two values. The x is going to be 41.67, the y is going to be 62.5. It'll look like this. And if we're wondering whether or not we just found a max or a min, we could actually use the second derivative test. Find the second derivative and then plug these in. And if we get a negative, it's the max. If we get a positive, it's a min. So if you're unsure when you're doing these, whether or not you actually got a max or a min, a lot of times it's forced into being 1. Like if we have a quadratic, there's only a single extrema there. It's going to be 1 max or 1 min. In this case, that's what ended up happening. If we wanted to put it another way, we would say that it's 125 all the way across, and y is 62.5.